IEMbase is an online knowledge base and decision support system for diagnosing inborn errors of metabolism. Pen the tool. Under the About menu, About IEMbase, we find an important overview. IEMbase is built from expert-curated profiles covering more than 1,500 inherited metabolic disorders. These profiles include clinical features, biochemical markers, and phenotype associations that are mapped to the human phenotype ontology and LOINC coding systems. This allows the system to use semantic relationships to generate a ranked list of possible diagnoses based on the symptoms we enter. Importantly, IEMbase focuses specifically on inherited metabolic diseases. However, it is not always possible to clearly distinguish between metabolic disorders and other rare conditions. This represents one limitation of the tool. In practice, this is a preferred tool when we suspect an inherited metabolic disorder, especially when routine pathology and biochemical results are available. In this tutorial, we are going to demonstrate the Search IEMbase tool, which you can also access from the home screen, and we'll focus on the Mini Expert tool. Let's work through a case. An 8-month-old male presents with progressive developmental regression, having lost previously acquired milestones, including head control. This is accompanied by marked hypotonia and lethargy. There is also a history of chronic diarrhea since early infancy and poor feeding. Newborn screening showed a mildly elevated C4 acylcarnitine, but a primary screening condition could not be confirmed. In the Mini Expert tool, we enter the main clinical features. Start with developmental regression, next, hypotonia, then chronic diarrhea, and finally, lethargy. At this stage, we will not yet include the biochemical marker. There are two search options. The first is the relaxed search criteria. This allows the system to include conditions where the selected biomarker may be elevated in a different sample type, for example, urine instead of serum. This is the option we use most of the time. The second is the strict search criteria, which eliminate any resulting disorder that do not contain any of the input biochemical features or clinical symptoms. In most cases, this is the preferred option. Next, we select Match and choose the extended search, as the results will in any case be ranked with the closest matching results displayed at the top. The initial results show several conditions. These are mainly cobalamin-related disorders and mitochondrial diseases. However, it does not actually include the condition that our patient suffers from. This illustrates an important point. Non-specific clinical features, as used here, are often insufficient to reach a diagnosis. This is where additional pathology and metabolic results can be of significant value. We are now going to refine the search by selecting Edit and add C4 acylcarnitine, mark it as elevated, and run the search again. The differential diagnosis now includes ethylmalonic encephalopathy, a mitochondrial disorder, SCAD deficiency. We can now select a disorder to view more information. It starts with general information on the disorder, followed by clinical symptoms by age and biochemical markers. Highlighted rows indicate findings that are characteristic. To return to the previous window, click on Close Window. Do not use the back button, as this will reset the tool and you will lose your current session. Next, we use the Differential Diagnosis tool. We select the relevant conditions and click on Differential Diagnosis. The color coding is important. Yellow or purple means shared by all. Light shading, shared by some. No color, unique. Bold text indicate characteristic symptoms and biochemical markers. We use the expanded table to include all data and select the appropriate age group. Now the differences become clear. We can identify unique biomarkers and characteristic clinical features. For example, 2-methylbutyryl glycine is unique to ethylmalonic encephalopathy. And clinically, hemorrhagic diarrhea, petechiae, and acrocyanosis are characteristic. If needed, we can zoom in to clearly see bolded features. These findings can now be correlated clinically to further support the diagnosis. IEMbase also provides additional support. We can view recommended biochemical tests, which in this case include acyl carnitines, organic acids, and selected routine investigations. We can also check gene panels. For this case, the relevant genes include ETHA1, APO, ACADs. In conclusion, IEMbase is a powerful clinical decision support tool that integrates clinical features, biochemical data, ontology-based reasoning to generate a structured and ranked differential diagnosis. When used effectively, it can significantly improve diagnostic accuracy in inherited metabolic diseases.